Welcome, everyone. We're getting ready to start today's seminar. Today's seminar is presented by Dr. Chen of New York University. He'll be talking about robust online learning and its application to assortment optimization. But before we get started, I have a couple of quick announcements. So I just wanted to point out that if you'd like to ask a question of the speaker, please use the Q&A feature of Zoom. So that will be in the lower panel on your device. You should have the option to ask anonymous questions if you wish, and you should be able to also upvote others' questions if you have the same question and you want to have that answered as well. And then as the seminar continues, I'll relay the questions to the speaker, most likely at the end of the talk. Feel free to use the chat, but if you do have a question for the speaker specifically, please use the Q&A section. So this is our first seminar in our Thought Leaders series. And so I'd like to invite you to come back next week. We're going to be having Dr. Chen from Rutgers University. You can see this website. You can Google Thought Leaders Iowa if you want to find it. And this link should be coming in your chat in just a second as well if you'd like to take a look. And then we're going to notify you once this seminar series is over. We're going to notify you of all of the, when all of the videos, all 6 of them are available on YouTube. So please be on the lookout for that. So let me introduce our speaker today, Dr. Chen of New York University. He comes to us from Carnegie Mellon University, where he got a PhD in the computer science department there. He also did a postdoc at UC Berkeley. And he moved on to a tenure track professorship at Stern School of Business at New York University, where he's currently an associate professor. He's a recipient of the NSF Career Award, which is a great honor for someone fairly early in their career. And he's done a lot of different things in his research. In particular, he's been supported as well by Google, Facebook, Adobe, and several other companies. He was also featured a couple of years ago in Forbes' list of 30 under 30 in science. And so we're very, very happy to have Dr. Chen present his research with us today. And so Dr. Chen, I'll hand it over to you.
Thank you very much for the invitation, and thank you for Sam's introduction. It's my great honor to present here in this great seminar series. So I will share my screen. So today I'm going to talk about robust online learning with application to assortment recommendation. I will give a very gentle introduction about some of overview of some of my projects on online learning. And then I will zoom in to particular one for the assortment recommendation. So it's kind of an online recommendation and see how robust statistics can play a very important role in that. Okay, so my research is pretty much focused on online learning and decision making. So actually, we know the classical statistical machine learning really facilitates understanding of such a given data. But understanding some static given data is not the ultimate goal, especially for many business applications. So for business application, we really care about decision making, and all business facing these challenges of decision making every day. For example, decision on prices, decision on recommendations, decision on tradings, and we'll give some examples on that. So we really focus on online learning and decision making, which involves a sequence of interactions between the platform and many agents. So this is a kind of a a typical framework of the problem I'm always been working on. So here is the online platform. You can just think it, for example, it can be Amazon, and the customer comes into the platform and whose purchasing behavior and or browsing behavior, we can usually adopt some probabilistic model to model that. And the online platform need to give the customer a certain kind of a decision. And for example, this decision can be price, decision can be recommendation. And what the online platform and the customer will react to this decision. So for example, given the price, he can choose to buy or not to buy. Given the recommendation, he can choose to click, not to click. And then the online platform will collect, first of all, he will collect the revenue from the customer. And they may also observe some customer purchasing behavior. Okay. So here, this kind of a framework where really connects machine learning and decision making. So in particular, the underlying probabilistic model for characterizing the customer behavior is usually unknown, and we usually need to learn it on the fly. And this is where the machine learning comes, where the machine learning is really good at trying to estimate the parameters of some underlying probabilistic models. But of course, there always being a challenge, and this challenge will be like one of the main focus of today's talk is that like it's very common to using some probabilistic model to characterize the customer behavior, but there always been some customer like irrational customer, they will never following this probabilistic model, so that the robustness becomes a very important like a challenge. And on the other hand, as I mentioned, for the online platform, the real-time decision-making need to be made for every arriving customer. So I will give some applications at the beginning, and then as I mentioned, I will zoom into one particular problem, and we'll see like how we address this problem. So for example, one thing that we'll consider in today's talk is what we call the online recommendation. And especially we consider a special form of online recommendation where we'll apply to substitutable products recommendation. So what do I mean is as follows. So for example, in the Amazon, and you search for headphone, and it will give you like certain, kind of choices or like alternatives recommendations. And the substitutable products means that we usually consider a scenario like the customer will only buy one product and only one product in today's like purchase. In this purchasing session, it's very unlikely he will buy like 2 headphones at the same time. Of course, the customer can say, I don't want any purchase and just leave the system. That is completely fine. But if they want to make a purchase, we just assume that they will purchase like only one product. So that's what we call it like substitutable products. And we're like using the machine learning and the choice modeling from the economics as the learning the customer purchasing behavior. And this is another like very interesting related application for this, what we call the assortment optimization, is that it's called Stitch Fix. It's another, like a very interesting platform where like the customer can subscribe their membership and tell them like their style and their fashion, and then the Stitch Fix will mail like a kind of a box to the customer every certain time or period. And for example, the winter comes, they will like mail a box which contains like several different kinds of sweaters and some other like accessories. And the customer can look at this box and maybe leave one item that he or she really likes and then return the rest of the sweaters. Okay. So this is kind of, but the key challenge here is as a business, what kind of the clothes you want to put in the box and send to the customer. So I have been working on this assortment optimization. There are quite a few papers I just listed here. And today we'll zoom into like this problem and talking about like the robustness in this kind of assortment optimization. Okay. But before that, I was talking about some other applications, like fit into this framework of online learning and decision making. So for example, we call it like one-shot dynamic pricing. So actually, as we understand, like for this kind of for several kind of online platform, and we really need to like determine the price, okay? And to determine the price, we need to understand the customer sensitivity with respect to the increase or decrease of the price. And usually we can learn something we call the demand function, which you can understand given a certain price, what will be the customer purchasing probability. Okay. So usually like traditional like kind of a dynamic pricing involves like learning this kind of a demand function and making the optimal price based on the estimated demand function, trying to maximize the revenue. However, there are certain cases, for example, for some product, I take an example of this is kind of the largest kind of online supermarket in China. It's called Tmall supermarket. And for example, in some like some items, the weekly sales is only 4. Okay, it's very low. It's kind of a low sale product. And for this kind of a low sales product, then it becomes very challenging to learning the demand function that characterize the customer behavior with respect to the price. So what I did is that we consider like a clustering-based dynamic pricing algorithm, which will automatically cluster the products that share the similar demand function. Okay, so that we can cluster them, and in this sense, we'll have like more like training samples, so that we can estimate the underlying demand function more accurately. Okay, so this is just another example of online learning. And the final example I will present is also like I feel like a very interesting application, which is called crowdsourcing. Okay. So crowdsourcing is essentially it's a problem-solving process where a large number of tasks are outsourced to a distributed group of workers with different expertise. And one example is like Amazon Mechanic Turk. So basic idea is that you have some task, for example, image labeling task, and you can distribute this task to all the workers on the internet, and they will help you finish the task, and you will pay them a little bit of money, for as a reward. And for example, in this Amazon Mechanic Turk, back into 2012, there has already been more than 500,000 workers from 190 countries, and this number is growing a lot during the past 10 years. And the Mechanic Turker can do a lot of jobs. For example, image classification, URL ranking, opinion gathering, and proofreading. And actually, I would say the cross-sourcing is the main driving force of the success of deep learning. So this is a very famous data set created by Professor Fei-Fei Li from Stanford University. And actually, in 2009, the data set contains 40 million images across more than 20,000 different categories. And the question is that, for such a large data set, the traditional machine learning methods are very popular, back 10 years ago, support vector machines or boosting, they just cannot achieve desirable performance when they're facing more than 20,000 categories. And then the people propose AlexNet and all this kind of convolution neural network based deep learning algorithm and achieve great success on this kind of a data set. But to collect this data set, actually the natural question is that how do you obtain this more than 20,000 categories, classes? And actually this is achieved by using the technique of cross-sourcing. So let's just give you an example, how the cross-sourcing works. For example, this is a very interesting data set people call the Galaxy Zoo, where the telescope takes the pictures of a galaxy for every second, and the people just want to say trying to ask the workers to get the shape of the galaxy. So there are many different kinds of shapes. So for the simplicity, as an illustration purpose, I only consider two different shapes. One is called the elliptical galaxy, and the other is spiral galaxy. Okay? So the cross-sourcing works like follows. So you have pictures, and you can distribute the pictures to the workers. And so there's a worker sitting in front of the internet, and the workers can give you the feedback. Okay, so this feedback does not necessarily to be consistent, because we understand some workers are good, some workers are not reliable, and even some workers can be just a robot trying to give as much answers as possible and trying to earn quick money. So given this kind of inconsistent result, you probably need to aggregate this result to infer the true label of the image. So for example, what you can do is by majority vote. And you can do sequentially for all different images. Of course, there is a challenge. There's no free lunch here. So you need to pay the worker, a certain amount of money, no matter the labeling is correct or not. And actually, it's very difficult even to tell whether the image is the labeling is correct or not, because the final inferred answer is usually based on some aggregation from different workers. Okay, so there is also a budget into consideration. So for this kind of online learning problem, the goal is to infer the true label of each item, infer the expertise of each worker, and have a very effective budget control. So the real challenge you can consider in practice is that how do you adaptively select the next worker? And because you have a budget constraint, so the question is that when to stop the data collection process. So for example, if you collect the 3 labels, they're all positive, you can probably stop here. But if they are inconsistent, say 2 positive, 1 negative, you may consider collect another 2 labels. And at the end, at a certain point, you think probably we should just stop here, because it's just can waste me too much money. And the final estimate is that how do you combine answers from different workers to infer the true label? So there are some papers here. I've been working this a lot, and some works I just want to mention is joint work with Ji-Han Lin. He's a professor at University of Iowa, and we have working a lot on this direction together. Okay. So this is just a very a brief introduction of this online learning platform and the potential applications I've been working on. And now I was zooming to one particular application, and I was thinking about what will be the main challenge in this online decision making. So as I mentioned, most online learning algorithms are built on certain probabilistic model. So for example, in the pricing, the dynamic pricing, we're assuming this kind of underlying demand model. So this is the price, this y-axis is the price and x-axis is the demand. So as we mentioned, when the price goes up, so if you can see the price goes up, the demand, you can understand that purchasing probability will decreases. Okay. So assortment optimization also assuming there's underlying choice model we'll introduce a little bit later. So this is kind of underlying probabilistic model. For example, this is a non-parametric function, but we'll assume there is such an underlying non-parametric function. But as like a very famous statistician, George Bock said, all models are wrong, but some are useful. So in practice, you'll never expect every customer just to follow this kind of a demand function. So for example, when you talk about like luxury product, it's very like sometimes even you have a higher price, the people are more willing to buy it. Okay, so it will be contradiction from the typical demand function. You assume that when the price go up, the people's willingness to buy it will decreases. So the question that naturally arises, which is that what if the customer does not behave according to the underlying assumed model? Okay. So the main topic of today's talk is that we are trying to deal with model misspecification and propose like online learning and decision-making framework. So for example, we can apply. So this is a very general modeling tool and some very general concept. So we can apply this kind of framework to, like, for example, assortment optimization I just mentioned, and it can be applied for dynamic pricing. So actually, I have a few papers on that. The first paper is we call it robust dynamic assortment optimization with the presence of the outlier customer, and it's a joint work with Akshi from Microsoft Research and Yining Wang, who is a professor at the University of Florida. And also a second paper is dealing with like dynamic pricing with demand learning, and it's a joint work with Yining Wang. So, and today's talk will focus on like the first one, which will focus on the application of assortment optimization. Okay, so but before going to details of application, I will first introduce a general framework, like how the people handling like robust synthesis. So as I know, like many people here, like are really the expert in robust optimization. However, if you think about like this very complicated multi-stage decision with learning, like the designing an effective robust optimization algorithm can be very challenging. So we will consider some new models, like we borrow from robust statistics. So I will use like 1 or 2 slides to just give a very brief introduction of robust statistics. And this is a very famous model. It's called the Huber's epsilon contamination model, proposed by Professor J.P. Huber in 1964. Okay. So the idea is very simple. You consider like there are NID observations from a mixture distribution, so x1 to xn. So they are generated in the following way. So it's kind of a mixture model with 1 minus epsilon probability. They are generated from a typical distribution. We call it p theta. So you can think it's just like a true model or typical model with the unknown parameter theta. For example, you just consider it as a normal distribution with the mean theta, standard deviation 1. And with epsilon probability, it will be drawing from like an outlier distribution Q. And this could be any assumption on this outlier distribution. This can be, like a very heavy tilt. It can be, doesn't have even like say the first moment condition. And this epsilon is we usually call it corruption proportion. But in general, we do not assume, like which observation, you do not know like which observations are outliers. So you just see like x1 to xn, but you don't know which one is drawing from this typical observation, which is drawing from this outlier distribution. Okay. And the question is that given x1 to xn, the question is that how do you estimate theta? Okay. So as we understand, if you have no corruption from statistical 101, we understand we should just estimate this theta by just taking a sample mean. Okay, as you take the average of x1 to xn. And this has a lot of like nice statistical property like asymptotic normality and efficiency. However, when there is an outlier distribution, a little bit kind of a corruption, can just arbitrarily destroy your sample mean, right? So because we know like the sample mean is very sensitive to the outlier. So the question is how to handle the corruption. And actually, a very natural idea in robust statistics is that just taking the instead of taking the sample mean, we just take the sample median. Okay. And we can even prove some certain high probability bound where like with high probability, the estimate the sample median, subtract this mean, subtract this true underlying parameter, will be bounded by some epsilon plus like 1 over square root of n. So if you can see this bound, this epsilon is a kind of outlier. And this 1 over square root of n is, like the standard parametric rate. And this kind of form of bound you will see again like in today's talk for our like specific application. Of course, like this is for like a 1-dimensional case. And when the theta is higher dimensional, like traditionally, this problem becomes much more difficult. Traditionally, people consider like what we call two key steps, and actually, but the two key steps is computationally very difficult. So there's a lot of like hot machine learning algorithms proposed recently to handle this case, and this becomes a very hot topic in machine learning in the, like we'll see in the past 5 years. Okay. However, so this is just a very general introduction of this epsilon contamination model. But this model only applies to like static data, where x1 to xn are all pre-given. And so we will consider, how to extend this model to like a more general, like a Huber's epsilon contamination model to the online setting. And people indeed consider that, so we'll introduce that here. So our model is like the model is as follows. You have a finite time horizon from 1 to t, and each observation xt is either typical observation from p theta with unknown theta, or it can be from outlier distribution qt. And we allow this outlier distribution in the online setting. This can change over time. And also, of course, we assume that there is a kind of adaptive adversary, which means that the outlier time periods, okay, so when the outlier among these t time periods, when the outlier time happens, and the corresponding outlier distribution qt can be adversary chosen and adaptively chosen. So adaptively chosen here, I mean, it can be chosen based on the historical information. So this can be a stronger, like a notion as compared to the traditional mixture model-based epsilon contamination model, because the outlier can choose, when the outlier happens and what is kind of outlier distribution. So we only have one very simple modeling assumption, which is saying that we have called the bounded adversary, and where the number which we just assume like a number of outlier observations is at most epsilon t. Okay. Of course, if you have too many outlier, then you cannot learn anything meaningful from the underlying model. Okay, so I just want to mention this model has been also considered in the CS literature, for multi-unbounded, and we'll comment on that when we talk about related work. Okay. So we will see like how we apply this model to the dynamic assortment optimization. But just to give also another little bit introduction of this dynamic assortment optimization. So we are facing like the recommendation problem, and this recommendation problem is how to select a subset of substitutable items to maximize the expected revenue. So the key to address this problem is to really understand the customer purchasing behavior when they are given like a lot of alternatives. So we'll adopt this what we call discrete choice model from the econ literature, where when you have like a set S, so when a set of assortment is offered, what will be the probability the customer will select a particular item I? So we call it PIS. And there's a lot of like popular choice models, like for example, the classical one, like a multinomial logic model, and there's something called nested logic model. So I just want to show like how important this model is in economics. So like Professor David McFadden won the 2000 Nobel Prize in economics just for the development of the theory and the methods for analyzing the discrete choice model. So I will give like a very brief introduction of the simplest case of multinomial logic model, where you assume there are n products in the pool, and each product has a non-negative, like the mean utility. Actually, it should be more precise. It should be exponential of the mean utility. So that's a non-negative. And sometimes we just call it preference score for simplicity. So like V1 to Vn. So this is kind of, you can view like customer preference score for each for each product. And we assume here in the multinomial logic model, we assume all the customers are homogeneous. Okay. And the choice probability is characterized by PS, which is Vi, over 1 plus summation of Vj, J from all like the recommended set S. Okay. So and this 1 corresponding to no purchase. If no purchase, we're just assuming the utility is 1. Okay. And of course, given the choice model, how do you select the best products, the best set of products, the best assortment? And you can just maximize this combinatorial optimization problem, where the Ri is the revenue of the item I, and this PS is the probability of selecting item I when given the assortment S, and the summation will be the expected revenue when offering the assortment S. And we just want to find the best assortment that maximizes expected revenue. And of course, I just want to mention, usually in the assortment optimization, we will put a cardinality constraint K on this S. So because, for example, in Amazon, you cannot display like hundreds of the web page at the same time. You can only, display, I don't know, like 8 or 12 pages, like products at the same time. So this K will be just the upper bound. Okay. And this will be we call it S star, which is like the optimal assortment. But this optimal assortment, again, I just want to highlight, is based on the fact that you know all the utility parameters. You know all the utility parameter and the corresponding choice model. So I just want to mention, actually, you can also extend what we discussed today to the nested logic model, where the people just select in the hierarchical way, where this first select, like say, for example, codes, and then the category, and then select the particular codes under this category. So this is called nested logic model. And also there's like an even more complicated model, which you call it contextual logic model, where you consider like time evolving utility, where we can assume that the utility parameter is not only like based on the product, but also based on the time. And for such a case, we can introduce like a linear model to model like the utility parameter, where xti is, like a, sorry, we'll put the exponential here. So there is missing like the exponential of this linear function. So xti is that each time t, you observe like a d-dimensional feature of item I, and the beta star is the underlying parameter to be learned. And so, for example, this is like a whole bunch of sweaters, and for this particular sweater, some features. So this will be like a 4-dimensional feature vector. So some features will be static over time, like the color and style, but some features can change over time. For example, holiday and the ratings. And so this model can even enrich the classical multinomial logic model by considering like time evolving utility. Okay. So now this is kind of introduction of like dynamic assortment optimization. So as I mentioned, given the utility parameters, it's a very simple combinatorial optimization problem, and this can be solved efficiently. Actually, we'll talk about the algorithm to solve that, but this by some very simple like kind of fraction programming with some bisection search, you can easily solve this optimization problem, and it's well known in the literature. But as I mentioned, where the machine learning comes. The machine learning comes in the fact that in reality, the utility parameters are really unknown and need to be learned. So for example, in the fashion products, you don't have enough historical data to estimate the choice probability in the offline case. And there's a huge amount of literature considering this online dynamic assortment optimization. So the framework is very simple. It's just that you have a seller and you have a buyer. Okay. And the seller will offer like assortment at every time period, and the buyer will make a purchase. Or the buyer can just leave the system, so the corresponding purchase will just denote by 0. And we consider multinomial logic model for simplicity. And the buyer, like the seller observe the buyer's purchasing behavior, and then will revise his or her recommended set. And then the game continues. The buyer will make a purchase and go so on and so forth until at the end of like the last time periods. Okay. So in this kind of a dynamic assortment optimization, we need to develop like a dynamic policy that simultaneously learns underlying utility parameters v1 to vn, and also make the decisions on the assortment. Right. So basically the customer purchasing information will come to the buyer, and the buyer will using that to have a better estimate of the utility parameters, so that can make the better recommendation set in the next time period. Of course, for this online algorithm, what will be the benchmark? So if you remember, the goal of the seller is just like trying to maximize the total expected revenue. So this will be the maximization of the expected revenue. And as you can see, this will be the revenue for the J's item. And this will the probability of making a purchase for the item J, condition on the assortment. Okay, so of course, but the question that, if you want to maximize it, so for example, some algorithm give you the expected revenue like $200. Some algorithm give you the expected revenue $300. 300 is better, but you don't understand, how good it is. So usually in the literature, instead of like trying to maximize the revenue, we're equivalently saying to minimize the regret. So the regret is just essentially a gap from the optimal expected revenue. So the optimal expected, so this is the expected revenue from our policy, which generates a sequence of S1 to ST. And this will be the expected revenue for the optimal assortment. And remember, the optimal assortment is obtained by just solving a combinatorial optimization problem with the known choice modeling, which means that the known utility parameters. And this gap we usually call the regret. Okay. So this is the dynamic assortment optimization. But now we are ready to combine this application with the model robustness. So you can assume like a multinomial logic model, very popular in econ literature, people using that a lot. But still, like in many cases, the customer will not follow the multinomial logic model. So then it's very natural combine what we just introduced before. We can talk about this epsilon contaminated dynamic assortment optimization. It's just following the model we just introduced, each arriving customer can be either a typical or outlier customer. So here we just assume the typical customer makes the purchase according to the multinomial logic model, and the outlier customer makes the purchase arbitrary. And you can certainly extend this multinomial logic model here to like nested logic model or like a like time evolving contextual multinomial logic model. And there is a bound like adaptive adversary. So like arrival time of outlier customer and the choice behavior of outlier customer can be arbitrary. So why is this important? Because like only we can allow the arrival time to be arbitrary so that we can trying to characterize the clustered or consecutive outliers. And this is especially true in the holiday season. So in the like in November to December, you will see many kind of outlier customer purchasing behavior. And finally, we just assume like among like the t time period, the number of outlier customer is at most epsilon t. Okay, so I just want to mention a little bit about like the related work. So I have been working on dynamic assortment optimization for quite a few years. So their earlier work, and we first consider uncapacited multinomial logic model. So there's no capacity constraint for the assortment. And there's like a very seminal work from Columbia groups on like capacitated multinomial logic model. And we provide a lower bound and we extend to nested logic model and also like contextual or time evolving multinomial logic model. So this is the one direction on the dynamic assortment optimization. And there's another direction, as I mentioned, on robust like statistics. So the epsilon contamination model was proposed by Huber in 1964. And as I mentioned, there is a very trendy area in machine learning to propose computationally efficient algorithm when the underlying dimension of the parameter is high. And the people also consider extend this, like for the multi-armed bandit. For example, there's a work from like this is from Pan Gupta from CMU, and this is a work from like a Google research. But however, you cannot directly apply the algorithm to the assortment optimization because like if you apply to them, you will think like for all the possible assortment, and each of them will be like a possible arm. So there will be like n choose k. K is the cardinality constraint. There will be this many arms. So that's just this arm will be like n to the power of k. It's just too many. So that will be exploding your like regret. So that we need new algorithm to handle this case. So here is just like a summary of the technical results that we'll talk about in like today's lecture. So it's very interesting to compare to the case where there is no outlier. Okay. So as I mentioned, the Columbia group, for the no outlier case, they derived the upper bound like n times t, where n is the number of products and t is the total number of time periods. And this also matches the lower bound, which is the square root of n and t. And we show that in our previous work in OR lectures. Okay. And how about like if there is outlier? So for the lower bound, actually, it's very easy to establish. So for the outlier, when there is outlier, and the lower bound of regret should be epsilon t times square root of n times t. This epsilon t, because they are outlier, you have zero hope to learn anything from them. So you have to pay the price for being robust. So this comes to this epsilon t. And the second part, square root of nt, should matches the case where there's no outlier. So this is a lower bound. And what the upper bound we obtained in our paper is like epsilon t times k squared. So as compared to this term, we have actual k square factor. And this term is square root of ntk. So they have actual k factor. But usually in practice, we do not worry too much about this k factor because as I mentioned, this is the cardinality constraint of assortment. And usually this k is small. Okay. Because as I mentioned, for example, in Amazon, you can only display, like say 12 kind of products at the same time. So this k will be small. Okay, so now we are ready to go into the details of like this algorithm design. How do we like how do we achieve this bound? How do we achieve this upper bound? Is there any like interesting thing in this algorithm design? So okay, so what we adopt like a strategy we call the active elimination policy. So the idea is as follows. So we first divide in time horizon to epochs. Like 1, 2, this tau is the number of epoch index 1, 2, 3. And the length of the time period for the tau's epoch is 2 to the power of tau. And this is usually in the literature, we call it the doubling tree. Okay, which means the first epoch is 1 time period, second is 2, and then 4, 8. Okay. And the key part in this active elimination strategy is that we obtain an active item set, A tau. And this will contain like we call the good items. What does it mean? This means the true assortment, like the best assortment, S star we are knowing the utility parameter should be contained in this A top with high probability across all the tops. Okay. So the key two ideas in this active elimination policy, the first of all is that you're starting from all the potential products like N. There's a lot of potential, like products. And we are trying to remove the bad items where the items are likely to be within the optimal assortment after each epoch top. So after each epoch, you should do a job is trying to get rid of those bad items. And within the epoch, we should do some random exploration of active items, trying to learn the utility parameter. And the key part is that for each epoch, for all the epochs, we are trying to make sure the optimal assortment will star will be contained in this A tau with high probability. Okay, so this is like general algorithm design ideas and the framework. So the question, the more detailed question is that how do we remove the bad items? And also like within each epoch, how do we do the random exploration of active items and to learn the utility parameter? So let's first think about how do we remove the bad items. Okay, so we'll think about it in two ways, like from the front and the back. So which means that we'll first say like what will be the good item. Okay, so good item means that like if there is an assortment S that contains the item I, such that like it achieves like the maximum expected revenue without any constraint that containing the item I, so which means the item I is good. So in other words, you can think in this way. So what do I mean by a bad item? So the bad item means that if you force to include item I in your assortment, and this part is like the expected revenue you obtained without enforcing the actual constraint, like the item I is within your assortment. If there is a big gap, so which means the item I is rather bad and should be excluded. So more precisely, this is the optimal expected revenue when S, for the current active set that contains the item I. And this, of course, we do not know the underlying utility parameter. We cannot really obtain the expected revenue. So what we can obtain is estimated version of the expected revenue based on the current utility parameter estimations, V1 to Vn hat. So on the other hand, this part is the optimal expected revenue without this constraint. And this is something with kind of a confidence level. Okay. And so as you can see, this inequality just saying that if you include the item I to your assortment, and suddenly you get a big decrease in terms of revenue, and then what you should do is just the item I is bad. You should just exclude it. And this confidence level have like analytic form. We're not going into details of that. But as you can see, this will be increasing with epsilon. So which means if you have more outlier, then you need like a larger gap. That's very intuitive. And also like it's decreasing with respect to tau. So which means when you have later on, the estimation new hat becomes more and more accurate. So your confidence bound should be like shrinks. So for the details, I won't present the details of that. You can refer to the paper. But I just want to mention like two important things. First of all, this is a very simple optimization, although it looks like kind of a complicated. And later on, we'll show like how to solve it. Very simple optimization algorithm can solving this combinatorial optimization. And second thing that indeed to applying this inequality, we need to know the epsilon. Okay. So, but in some applications, for some application, you can try to estimate the epsilon from his historical data. But some applications very difficult to estimate the epsilon. So actually, there is a version of this algorithm where we can maintain like kind of a multi-layer elimination race strategy taken from this paper, and then you can apply that strategy, and then you can design adaptive algorithm so that without any information about the epsilon. So you basically maintain like a multi-threads of epsilon, and you coordinate with those threads and trying to get rid of those threads where you believe like epsilon for these threads is wrong. So there is an adaptive algorithm, but due to time constraint, I will not go into details of that. So this is how do we eliminate bad items, okay? And second thing that how do we estimate the utility within the epoch? Okay, this is very straightforward. So like we just have some random exploration strategy. You randomly select the active item I, and then you find the best assortment based on like include I in this assortment. And then you just record a few like summary statistics. For example, Ni is the number of times I was recommended and then was purchased. And N0I is the number of times like I was selected, but no purchase. And you can see like without the outlier, they follow this kind of a multinomial logic model. So a very natural estimation by VI, like by this VI, is just taking the ratio of this Ni and N0I. So of course, this is without the outlier. With the outlier, you need like to bound it more carefully, but we're not going into details of that. But the algorithm still holds that you can just need a little bit more careful in the analysis. Okay, and you can repeat this procedure after you estimate the utility parameter. You can repeat this procedure of removing the bad items. So this is just a summary. So first of all, like within each period T within the epoch, you randomly select the active item, and you offer the best assortment that contains I, and you record the number of times I was selected and purchased, and I was selected and no purchase. And at the end of the epoch, you estimate the utility parameter. You update your estimate of the utility parameter, and for each item in the like a current active set, you verify this inequality. Okay, just verify this inequality, and this R hat is based on the current estimate. And for those who satisfy this inequality, which means there's a big decrease of the revenue, and this item I should be removed. And finally, we just want to mention, how to solve this assortment optimization. So this is just writing this expected revenue in a more like closer form. And this is kind of a constraint of assortment optimization, but this can be easily done with a binary search scheme based on the paper from Pat from about 10 years ago. So actually the idea is very simple. I can just introduce by one line. So every time you're trying to test like a lower bound for this revenue, okay. So you just test whether it's a valid lower bound or not. And if it's a valid lower bound, you can increase it. If it's non-valid lower bound, you should decrease it. And you can manipulate this kind of a fractional programming a little bit, so you can get just get this kind of inequality. So whether this satisfied implies this just satisfied. Okay, so this part is based on I because I must be in the set. So we just put this on the other side. And for this part, you just want to see whether it's satisfied in this inequality. So you just need to find such like S prime with cardinality constraint k minus 1 because I has already been contained in this assortment. So that you just find the largest k minus 1 item with the positive values of this. Okay, you just find like k minus 1 largest item with the positive values on this term. So and if they're satisfied, this means R low is a valid lower bound, and so that you can increase it. So otherwise, you just decrease it. So it's more like a binary search kind of a scheme. Okay. So this is like the algorithm, and finally, I just want to mention like the just a recap of a little bit on the regret upper bound, which is epsilon tk square and square root of ntk, and the corresponding lower bound is epsilon t plus square root of nt. So as you can see, it's only off by like a factor of k, and this don't worry us too much because cardinality constraint k is usually treated as constant. But of course, for the technical perspective, this will be interesting question to how to get rid of this k. And finally, I'll just show you some very simple simulated experiment. So we compare our algorithm. In the non-adaptive means that you know the epsilon corruption proportion ahead of time, and adaptive means you do not know the corruption proportion. And this is compared to like the UCB algorithm and Thompson sampling algorithm. So those two algorithms do not take the robust model into consideration. So this doesn't mean the main purpose of this very simple simulation is to show that if the true model is indeed has quite a bit of outlier, it's very critical to take that into consideration. Okay, and we report the average regret over t time periods. So this is we have like 5% of corruption. So as you can see, our algorithm still as the time goes by, the regrets, like average regret decreases. But if you do not take that into consideration, you will find, like average regret will not decrease with respect to the time. And we can even like increase the corruption proportion to even larger, like 10%. So you can see under such a large corruption proportion, our method is still like kind of decreasing. But if you do not take that into consideration, the robustness into consideration, and this lines will be flat. The average regret will be flat. Okay. So now I think it's a good time for me. The time is almost up, so let me make like one slide conclusion, and we'll take the answers. The question answering. Okay. So so we talk about like online learning decision making. I feel it's a very important field especially in business, and it's not like can be easily handled by traditional machine learning or classical statistical machine learning method. And we talk about like online recommendation, dynamic pricing, and the cross-sourcing applications. And when you're trying to do this real like online learning decision making in real practice, the model misspecification happens all the time. So the robustness is critical. So in today's talk, we're basically saying that the extension of Huber's epsilon contamination model can be a very good framework for capturing outlier behavior. It's more rich than the like a 40 stochastic case, but also not as pessimistic as the 40 adversary case. And this is a paper that we discussed today, and this is the archive link. Finally, I will say, operation management is a very important thing. Like, for example, assortment optimization is a core problem in operation management. But when it's dealing with it, like the modern machine learning tools like robustness and many ideas in machine learning can be very useful. So that we're really trying to make a break for this problem, trying to combining like the machine learning ideas to solve like operation management problem. So thank you very much. I conclude my talk, and I'm very happy to take questions.
Thank you, Shi. Thanks for a great talk. I'm going to wait a couple of minutes to see if we have some questions come in. In the meantime, so just as a reminder for those attending, please just type your questions in the Q&A option down there. But I have a couple of questions that I can ask while we're waiting for some others. So I was curious about the way that you modeled the customer behavior. So this idea of taking the Huber model and putting it in a dynamic setting. So you said that a customer either you'd get sort of a normal customer in one particular time period, or you'd get just a customer that was totally an outlier. I guess I was curious if there might be a different way to model it, or if you could discuss the different options that maybe you had when you were designing this, because it seems like maybe you could have a customer it's still a regular customer in a sense, but they just do something a little differently than before. So I wonder if you could address that.
Yeah. Thank you very much for Sam's question. I think it's a fantastic question. So here we model in this way. The customer is either completely typical customer for the 100% of like underlying multinomial logic model, or it's an outlier customer. Of course, we do not put any restriction on the outlier customer. They can happen anytime, and their outlier behavior can change from time to time. But still, another like a very interesting way is trying to say revise this multinomial logic model, assuming for example, every arriving customer can have a little bit deviation from like multinomial logic model in terms of their purchasing probability. Okay, but I think it's a very like a very interesting route. Actually, in classical statistics, people also consider that. So instead of assuming this mixture model, that people assuming like it's coming from some very heavy tail distribution. But in this dynamic problem, I think there will be some difficulty. The first one is that like you need to finally, if you choose such a way, you're assuming. So for example, your real like a customer like choice behavior will be deviates from the right hand side on the multinomial logic model by some gap parameter, and this gap parameter will come into the final regret. This just makes analysis much more difficult. I think that's certainly something I'm like very worthy to look at. And indeed, I have been done like one work. I just want to mention that. In terms of this dimension, we have done something, so for example, we call it like non-stationary stochastic optimization, which means that, there is some, so we allow certain like deviation from the underlying, like the objective function can change over time. But of course, we cannot allow it to arbitrarily change. We need to put a certain constraint on the like adjacent, like change of like two objective functions. So this is kind of one step towards that, but I would just say like there will be some technical challenge, but it's a very good direction to look at.
Okay, thank you. So we do have a couple of questions. Let me ask those on behalf of the attendees. So have people considered a Bayesian framework to solve online assortment? What's the suitable performance metric similar to regret for Bayesian setting?
Yes, it's a very good question. So I strongly recommend for those who are got interested in this, so this paper, like Thompson sampling. So that is not exactly the Bayesian way. It's just like you still have the frequentist model, but you more like using a Bayesian online learning approach to handle that. I don't see like a 40, so, but this has the regret, kind of the regret analysis in this Thompson sampling. This has certain Bayesian flavor. But the model itself, I think, is still frequentist, but it's just like using a kind of the online learning strategy rooted in the Bayesian, like Thompson sampling, to solve that. I do not know, like the exact, the completely Bayesian treatment of the online assortment optimization. I think it's a very interesting direction to look at.
Okay, thanks. One other question. Since you benchmarked against the MAB algorithms, the attendees wondering if reinforcement learning is also applicable.
Of course, first of all, I want to say all the multi-embedded can be built as a special case of the reinforcement learning. But the challenge here is that there's still so many actions. Okay, so even you put on a reinforcement learning framework, the challenge didn't change. The main challenge here, for handling this kind of a recommendation, is that there's just so many possibilities. And if you apply any traditional reinforcement learning technique, you still need to handle this huge action space. And the question that there is a lot of policy gradient method. We can parameterize the action, but it's very unclear here for this combinatorial set of actions. How do you parameterize it and adopt any policy gradient method? I think here is the key challenge. It's not whether it's like a RL or like a MAB. It's more like how to handle in this excessively large action space.
All right, so I think I have one more question, and maybe if anybody else wants to type anything in. So I had a question about the epoch size. I understand that the epoch size is fixed based on that parameter tau. Is that understanding correct?
You mean epoch?
Yes.
Yes. So we're just using like a very standard doubling trick in like this kind of online learning. Like the tau is just iterates from 1 to n, and the t tau is the time period within each epoch. So within each epoch, we just do like the like the learning of the utility parameter. So which means that first time we you can think about, we use 1 time period trying to learn the parameter, then we use 2 time period to learn the parameter, 4 time period to learn the parameter. So like the gap of like removing the item becomes longer and longer. But it's intuitive because later on you really need a very, as the time goes by, like your estimation becomes more and more accurate. You need like very accurate estimation before you can confidently saying that this item is bad, I should exclude it.
I see. Thank you. That answers my question. I had a misunderstanding. I thought that all the epochs were of the same size, but I see now that they're growing.
It's a kind of a doubling trick. Yeah.
Awesome. All right. Well, let me, if I may, if I could share my screen real briefly, and I'll wrap everything up here. So I just wanted to thank everybody for coming today. Thank you, Professor Chen, for great talk and for participating. And thanks to all the attendees for coming. And please be on the lookout for the Thought Leader seminar next week. Thank you, everybody.
Thank you very much. Thank you, Sam. Really appreciate it.
Thanks.